Hi, welcome to this demo of a new feature in MQ912 called Uniform Clusters. In the video, we're going to demonstrate the main capability of uniform clusters, which is that you can have application connections evenly distributed across a group of queue managers automatically, where the group of queue managers communicates amongst itself and tells applications to reconnect elsewhere in order to maintain an even distribution of connections. We're going to have a quick look at the new JSON format CCDT, which was also introduced in 9.1.2, and how you can use that to help set up a uniform cluster scenario. And finally, we'll look at the way you can now specify the name of an application more easily and use that naming to decide which applications are going to be distributed across the group of queue managers. The video assumes that you already have an MQ cluster of 3 queue managers. If you want to follow through all of the steps in the demo, you'll need 3 queue managers that are already clustered. You'll need to know the name of the cluster you have put them in. And what we're going to start by doing in the video is stop the 3 queue managers. I've got 3 called class QM1, class QM2, and class QM3. So the first thing we do is stop all the queue managers. We then, to turn on uniform cluster features, go into the qm.ini file for each of the queue managers and set a tuning parameter. The tuning parameter is called uniform cluster name. What that tuning parameter does is tell the group of queue managers, while they're already clustered, it tells them that they have been configured in a uniform way, and therefore any applications connecting to any one of the members of the cluster can have any application instance redirected to it, because the queue that application is going to use is defined on all the queue managers. Any security settings are consistent across the queue managers to allow applications to connect to any one of the members. So the uniform cluster name tuning parameter is effectively a way of saying, I have configured an MQ cluster and I have configured them in a uniform way, and that enables some of the features I've described. So we go into the qm.ini file, we set the uniform cluster name in the tuning parameter section, and we set it to the value of the MQ cluster you have set up. Now that needs doing on all 3 of the queue managers, as you can see I'm doing here in the video. And once that's done, we simply restart all of the queue managers, and then we'll go and look for a message in the AMQ error log file to show that the queue managers have joined this uniform cluster. So as you can see, I've added the tuning parameter to all 3 queue managers. I'm now restarting each of the queue managers in turn. That's QM2, we'll just do cluster QM3. So now we've restarted all 3 of the queue managers. We now need to just check that each of them has registered that setting. So we're looking the AMQ error logs to see that there is this new message, AMQ 9983, joining uniform cluster, and it'll actually include the name of the cluster it's joined. So we'll go and check that in 1 or 2 of the queue manager error logs. If we do a quick search, I've actually searched for uniform cluster, but you could search for the precise error code 9983 as well if you want. Right, so there we can see joining uniform cluster and then quotes my cluster, which is the name of my MQ cluster. And that just confirms that the queue manager has registered that it's in a uniform cluster and the name of the cluster to be a part of. Now it's worth saying at this point, as we check just one of the other queue managers to make sure that it's also in the uniform cluster, it's worth saying it is possible to do more complicated things than I'm showing in this demo. You could overlap these queue managers into other clusters, but the primary aim of a uniform cluster is to have a smallish group of queue managers working together to provide the same queuing services to a number of applications. So if one of the queue managers is taken down for maintenance, the applications can be reconnected to any of the other members. So for this demo, it's worth just having a small development cluster where you're not doing anything complicated like overlapping the clusters or anything like that. So let's have a look now at the JSON CCDT we're going to use to connect our applications. I've just opened the ccdt_schema file, which is installed in the opt_mqm directory under lib on Unix platforms and under bin on Windows platforms. You can see this schema that I'm scrolling on the left can be used with any JSON tooling to create a JSON CCDT schema, JSON CCDT file. So the schema lists all of the valid properties, the ranges they can have, the types that they are. So you can use that schema to define your own JSON CCDT. And what I'm going to do now is open up the CCDT I'm going to use in this demo. Now I've got two different CCDTs, one for my putting applications, which aren't the main focus of the demo. The putting applications are really just going to run in the background, making sure messages are going to each queue manager. And then the getting application. We'll talk about the getting application in a moment, but looking at the CCDT for the putting applications, I've got a QM group in my CCDT. So in the QM group are each of the three queue managers, but the queue manager name for those entries is class group, not the queue manager name, and that's a basic CCDT QM group feature. One of the other key differences you'll see here is that the channel I've defined on each of my queue managers has the same name. Now this is an important benefit over the previous binary version of CCDTs that we used, in that you can now have channels with the same name in your CCDT. And that obviously means the channel in your queue managers can be the same, and that makes the configuration of multiple queue managers a little simpler. So we've got the queue manager group in the CCDT. Also in the CCDT is an individual entry for each of the queue managers. So you'll see here that these entries look similar to the queue manager group, but they are named with each specific queue manager. That's because the queue manager group will typically be used for the initial connection from the putting application, and we get the workload balancing, the distribution of the connections across the group when they first start. The individual entries are used so that when one of the applications gets asked to reconnect to a specific queue manager by the uniform cluster, and that's one of the main new features of uniform clusters, it has the details to get to exactly class QM1 or class QM2 or class QM3. We'll look at that in slightly more detail with the getting applications in a moment, but first let's start our putting applications. So we make sure we set the CCDT environment variables, MQ_channel_lib and MQ_channel_table, and that's exactly the same as you would have done previously for a non-JSON CCDT. And we're going to use the putting sample AMQSPHAC, which is the highly available putting sample. That's because that sample has the MQ_CNO reconnect option already set for us, and we need the MQ_CNO reconnect option set so that an application can tell a uniform cluster, I can be reconnected elsewhere. You're able to move me to another queue manager if you need to. So I'm starting 3 instances of AMQSPHAC. Again, these aren't really the focus points of the demo. These are just to make sure that messages are being placed on the Q1 on each of the queue managers. What we're going to focus on in a moment is the behavior of the getting applications in different scenarios in the demo. So let's start 3 instances of AMQSPHAC, and then we're just going to minimize those windows and let them run in the background. So one thing we'll just do is make sure that by using runMQSC to connect to a couple of the queue managers, we'll just check that there's a connection to each of the queue managers from AMQSPHAC. This is on class QM1 first, and I'm using the display connection command, discon, to check connections into the queue manager where the application name or the Apple tag is AMQSPHAC. We'll be using this command quite a lot through the demo to check where the getting applications are connected to. So it is worth familiarizing yourself with the display connection command in RunMQSC if you don't know it already. So we can see that we've got one instance of AMQSPHAC on QM1. We'll just do a similar check on QM2, and we might just check also that if we look at the queue depth of Q1, we have actually got messages accumulating on that queue. And then we'll finally just do one last check on QM3. If we just check on QM3 that again, the depth of Q1 is slowly increasing, I think we'll be fairly confident that we've got an application connected to each of our queue managers. So while we minimize those putting applications, we're going to reset and create 3 new terminal windows for the getting applications. And we're going to look at the JSON CCDT for the getting applications because it's slightly different. I've created it in a slightly modified way just for the purposes of the demo. So you'll see we have a queue manager group in the getting application CCDT. We also have an individual entry for each queue manager. But the queue manager group is modified intentionally so it only has the channel for one of the queue managers, class QM1. That will make sure when the getting applications initially connect to the group, they will always go to QM1, and that will force us to demonstrate the uniform cluster moving the applications when it realizes it needs to some of the other queue managers. So you'll see we still have an individual entry for QM1, QM2, QM3, and that means when the cluster tells an application to go to one of those queue managers, it knows how to get there. So we now do the same thing we did for the putting applications. We make sure the environment variables are set, and we're going to start an instance of AMQSGHAC, the getting version of the HA sample. And because of the CCDT I have set up for the demo, we'll go and check that initially every one of the 3 applications starts out by connecting to class QM1. So just before I actually start each of my instances of the application, I'm setting up the environment a little bit because shortly after they connect, the uniform cluster will detect that the applications aren't evenly spread across the queue managers and will start moving them. So I want to be able to show you that process before they all get reconnected. So I'm setting up a few commands. I'm setting up the display con command to show the instances of the AMQS GHAC application. You can see we've got no instances on QM1 at the moment. And now we start all of the instances of GHAC. They start consuming from QM1. And if we run the command again in the RunMQSC environment, you can see now we have 3 applications connected, which is what we expect. So if you keep an eye on what's happening in the terminal windows for the getting applications, at some point the uniform cluster will detect that there are 3 queue managers, but the 3 applications are all currently connected to one of them. And it will start to tell those applications to reconnect elsewhere. So let's keep an eye out for a reconnect event happening. Okay, so we've got 2 reconnect events happen there on the top 2 terminal windows. So what's happened there is the queue manager class QM1 has used the normal reconnect behavior that MQ's had prior to 9.1.2 with an additional bit of information, a hint as to where the application should reconnect. We've rerun the display connection command on class QM1, and now we only have 1 instance. And if we do the same command on class QM2, we will hopefully see that one of those applications was reconnected to class QM2. Okay, there's our instance running on class QM2, and we'll now do the same thing on class QM3, and hopefully that will then show that we have now automatically achieved a balanced environment where there's 1 application per queue manager, not 3 applications on a single queue manager. There we go. So that's shown how by using a correctly configured CCDT, turning a 3Q manager cluster into a uniform cluster and using an appropriate application with MQCNO Reconnect set, a queue manager in the cluster can tell applications to reconnect to a specific other member of the cluster and over time achieve a more balanced environment. What happens now if we take one of those queue managers down for maintenance? We'll use endmqm-r to shut down class QM3, and you can see the application that was connected to class QM3 has now reconnected in the way that it would have done with any normal endmqm-r scenario, any normal failover. So it's failed over to one of the other queue managers. And the important thing here is not the failover case when the queue manager ends, but actually now what happens when we recover that queue manager after some maintenance. Now, typically you would need something custom in the application once a queue manager has come back online to get one of the applications to move back to start servicing class QM3. And that can be quite a tricky thing to do, depending on the application environment you're using, depending on how much custom code you're happy to write. But out of the box, once an application is happily connected to a queue manager, it won't typically fail back to another instance before MQ912. However, with the uniform cluster, because we have that checking in the background across the queue managers to say, is there an even distribution of applications across the cluster? When we bring class QM3 back online, the same set of steps will take place. The cluster will detect that there isn't an even distribution of applications. You can see no applications on class QM3 yet, but if we give it a few seconds, we will hopefully see that the cluster will ask one of the instances to move back to class QM3 completely automatically with no intervention, no custom code in the getting application. Okay, there we go. We can now see in the middle terminal window that application's had a reconnect event from the queue manager. And if we now look at the connections to class QM3 again, using the display connection command, there we go. We've now got an instance of AMQS GHAC connected to class QM3, and all we did was take it down for maintenance and restart it. So a related feature in 912 is the way that we can now customize the application name that an application presents. So what we're going to do in this part of the demo is we're going to run a single instance of an application, a getting application. This is the same cluster. We're going to run a single instance on Linux, and you can see here that we've got an instance now running. The sort of blank section with the note to the right of the screen is where we're going to have a Windows command prompt. While my VM is in focus, the Windows command prompt drops into the background. So we're going to switch back to it, and it'll come into the foreground as and when we do things with it. So we can see that cluster QM1 has got both one of the putting applications and one of the getting applications. That's what we'd expect with one Linux application running. So what happens if we connect a Windows application to the cluster, exactly the same application? You might think that the cluster would automatically rebalance that application to one of the other queue managers. So let's see what happens. This is using the same CCDT we used for the Linux environment and exactly the same AMQS GHAC application. So we connect the Windows version of that application to the queue manager group in the CCDT, and we'll see where it ends up. It should end up on class QM1 because we've still got that slightly modified CCDT to force initial connections to go to class QM1. And you'll notice in running QoC in a minute, I've used a slightly different where clause. I've used a display connection command where the channel name matches a certain value. That's to make it a little easier to display the applications we're interested in. Okay, so we've now got a Linux and a Windows application connected to the cluster, and we should see if we run our command again that they're both connected to clustqm1. Okay, there we go. We've got two GHAC instances, but if you look at the Apple tag values of the two of them, they are slightly different. One of them just says AMQS GHAC. The Windows one has part of the path to the sample and then .exe on the end, so it's slightly different. And actually, that means that because the uniform cluster balancing is based on that Apple tag value, the uniform cluster will never rebalance those instances because it doesn't think they are the same application. So the application name, the Apple tag in this view in running QSC, is the key on which the uniform cluster will decide how evenly balanced an application is. What we'd like to do is be able to say, well, actually, these two applications are the same. They just happen to be on a different platform. And a new feature in 9.1.2 makes that far easier to do. What we can do is we can set, in a number of ways, the application name that an application should present to the queue manager. Now, in this demo, I'm going to set the environment variable, MQ Apple name. But there are various ways of setting the value. You can set it in the client.ini file. You can set it on the CNO. On different application runtimes, you can set it in things like the connection factory for JMS. So in this demo, we're going to set the MQ Apple name value to AMQS GHAC, connect it again, and rerun our command. And now you can see that we've got two instances that look identical, AMQS GHAC. And that means that the uniform cluster rebalancing logic can consider those two as identical applications and use the same rebalancing logic we saw to rebalance one of them. And there we go. We can see that the Windows application has been asked to reconnect in exactly the same way we saw in the other part of the demo. Coincidentally, we've actually seen the other Linux application get reconnected as well. That's a slight nuance of the way I've set up my environment. The important thing is here that for this demo, I've only used two application instances and I've got 3 queue managers. And typically you would have at least as many applications as queue managers. But because I wanted to mainly demo the way that you can make Windows and Linux applications present as the same thing, that's a slight nuance of the way I've set things up. So we'll see that on clustqm1, we actually haven't got any getters now. We've got the putter. And if we look at clustqm2 and clustqm3, that's where our two instances have been reconnected to. So like I say, you would normally want at least as many applications as queue managers to make sure that every queue manager is being serviced. This is a slight nuance of the way I've set up my demo. So there we've got one of them on clustqm2. And one of them on clustqm3. So using that MQ Apple name feature, you can now present applications to the queue manager in a consistent way, and that's a very important part of making sure that uniform cluster rebalancing can work appropriately. So that's the end of the demo. Thank you very much for watching. There's more information in the Knowledge Center for each of those topics that we've covered. Please feel free to contact us on the forums if you have questions about how to set up a uniform cluster or more detailed questions about the different ways you might set them up. I hope that's been a useful introduction into the way uniform cluster rebalancing can work and give you an automatically even setup of application connections to queue managers. Thank you very much for watching.